All right, so probably 3 weeks overdue, but or at least 2 weeks overdue. But that's the way the cookie crumbles, so we'll just roll with it. Which is why I haven't necessarily given you a hard time with like the questions, because it's still instructive to try to come up with your own questions that may or may not be interesting. And I'll put that in a little bit different context in a second, because I do get what Maddie's saying, where what might be interesting to me might not be interesting to somebody else. I guess maybe I'm using the wrong term, interesting, but I don't think so. I think anything that's interesting to me should be interesting to everybody. Yeah, that's a true statement. Interesting is probably not the right word here, though, and I think that'll make sense here in a few minutes. Huh? That's definitely not the right word. That's a worse word.
Like usable guy or meaningful word.
Try to come up with the right word here in a few minutes after I kind of give it some context. All right, shut up, everybody, shut up. Don't until I tell you what I'm trying to get at here. So, what problem does data science solve? And I'm asking a little bit deeper question than when we originally asked this question, and we had a very good answer, very interesting answer that was, it paints a picture, right? Okay, but now we want to think about, maybe, actually I'm going to ask this question a little different. When do we use data science tools versus another tool? All right, and I think this is kind of where the challenge has been over the last couple of assignments is, we're trying to do everything in the context of these data science tools, which is what I wanted you to do. But the questions that have been asked in general aren't necessarily questions that require data science tools to answer. You kind of see what I'm saying? But there are questions that you could ask of the data sets that you have that would be explorable through the data science tools. So having said that, what kinds of things are data science tools good for?
We need to do forecast or prediction.
Okay, forecast, predictions. But can we do that with other tools? I mean, do you, when you're, let's try to come up with an example that's not based on, a real life data science example would be, let's say you are getting ready to drive in, next weekend, something like that. You might look at you might gather some data to figure out what your drive might be like and what time you should leave and things like that based on the weather. So, you would pull in data from weather forecasts, maybe some visualization maps, how much snow is getting in different areas and what time it's going to be there, so you can try to hit those areas at certain times. You never hit it at the right time, right? Sometimes it looks like it's going to be horrible and you don't hit anything, and then the place that was supposed to have nothing, you hit something. But that's really kind of a real life data science type thing, is you are the data, your brain is the data science tool. You're bringing data in and you're interpreting that data and giving some meaning to it, right? How else could you decide whether or not you're going to leave at noon on Sunday? If we're thinking about what's the right tool for the job for deciding how you're going to leave for your drive on Sunday. How do you choose to use the weather channel or some weather app or something like that for that? And what other data do you take into consideration?
I think you need to understand what trends you need to analyze in each case.
Okay. Well, when you say trends, what are the so let's come up with a strategy. We'll just do Thanksgiving as our example from last week. So let's say your family was having Thanksgiving at 7 p.m. Okay, so that was when dinner was. So now you have one constraint, that you have to be there by a certain time, right? Dinner's at 7 p.m. on Thursday. So showing up on Saturday morning, not going to cut it, right? A couple days late for the dinner, you need to be there by 7 p.m. Thursday. So now you've constrained your data. What are some of the things that could hurt hurt you getting there by 7 p.m.? Okay, one thing's traffic. What's another thing? Weather. What's another thing?
Time you leave.
Time you leave, because Any way you cut it, there is an amount of time that trip will take. Could be relative to the speed you're driving, right? Some people can make that trip a lot shorter if they're going to push it, but it's more than zero. Okay, so there's a lot of variables that are set things there. So if you take, and some of those aren't variables. So if we, let's just say we assume that we're going at a fixed rate of 70 miles an hour. The amount of time it takes to get there would be then a fixed amount of time, plus or minus 20 minutes or something like that, right? All right, so you might say, okay, well, it's going to take me 4 hours to get there if everything goes smoothly. So I guess best case, you have to leave 4 hours before you need to be there. That's if everything goes smoothly. Now you have to start thinking about traffic. How do you try to figure out traffic? Is there like a weather channel for determining traffic?
Oh, you can use Google Maps. Yeah.
Oh, you can use Google Maps, but now you have to worry, how does Google Maps get their data?
Trends.
Oh, sometimes it's trends. Tell me about that. Have you ever seen on the GPS, this is something that's been popping up a little bit more recently, it'll pop up and say that traffic is a little heavier than usual right now, right? That's kind of a trend where, hey, at 4 p.m. on Wednesdays, traffic usually is like this, but real-time data indicates it's a little bit worse than that. So if you were telling me, let's say I was heading south through Chicago, what would be the worst time to go through Chicago on a Tuesday?
4 and 6.
Like 6, like 5, 6.
PM?
Yeah.
So 5 to 6, 4 to 6 p.m., that'd be a pretty bad time. Any other times?
Probably in the morning.
Maybe 6 to 8:30, 6 to 9. Somewhere said that we kind of have a sweet spot maybe between. And what about lunchtime?
I'm not sure.
Not as horrible, but still not great, right? You wouldn't want to be going right through through Chicago on at noon on a Tuesday. So if you were planning your trip and you were heading south of Chicago from here, you would probably try to get through Chicago, enter Chicago around 9:30 or 10, get through Chicago prior to the lunch rush, and now you're south of there. If you can't make it that early, then you'd probably try to hit Chicago maybe around 2 p.m., get through Chicago before 4 p.m., something like that, and avoid the traffic. Why do you know that? A couple of you mentioned some times that you want to avoid Chicago. Why, do you just pull those out of a hat?
I've done it before.
Okay. Is that where your data's coming from? How many times have you done it?
5.
5 times? Okay, so it's a pretty small data set.
Yeah.
Maybe you were just unlucky.
Okay, also, it's like you can check.
Okay, well, so what makes you believe? How many of you have never driven through Chicago? Okay. Now, do you believe that this 4 to 6 p.m. thing is probably a true statement? It's probably heavier traffic then? Okay. Why do you think that's true?
It's a commonality for most cities because it's when work starts and gets off.
Okay, so people are getting off work around then, right? And when you have a big city with lots of people and lots of cars, and they're all leaving at the same time, you're going to have congestion. You're going to have traffic, right? You can try to get real-time data that maybe operates off of some things where it's going to say, hey, look, we're going to put, you look at the Google map, right? And it shows you, red where it's really slow and yellow where it's kind of slow and green when everything's okay. And we don't necessarily know. We're looking at real-life visualizations of data, right? But we don't necessarily know the source of the data. We don't know whether this is truly real-time or if it is real-time data overlaying on trend data. Maybe the starting point for a Tuesday for current traffic on Google Maps is what the average traffic was based on data collected over the last 6 months at Tuesday at this time. That's the starting point for the map, perhaps, right? That would make some sense. That Tuesday at 2 p.m. this week should be similar to Tuesday at 2 p.m. last week, should be similar to Tuesday at 2 p.m. the week before that. But the more points of interest, the more data points we have, the better, because you might have some weird Tuesdays. Maybe there's a Tuesday where it was a holiday, something like that, where it's an outlier. There's lots of data that, it's distinctly different than, other Tuesdays, something like that. Okay, so is it ever crowded on the weekends? What about Milwaukee? Do we have rush hour in Milwaukee? Yeah, it's not as bad as Chicago, but we have it, right? The time's pretty similar. Jordan mentioned that, we have some commonalities thing in cities of size. And I mean, really, it's probably relatives. Even a small town that has fewer roads, smaller roads, you don't have 6 lanes in each direction. You probably still have their own version of rush hour where you might be running 7 minutes slow or something because, everybody's on their way to work in the morning, something like that. But so Milwaukee, we probably could apply those same rules. The 6 to 9 a.m. or something might be, you might want to avoid 43. You might want to avoid 94, something like that. And really, those are the big question marks, right? So if I'm ever driving, I usually use my GPS to at least give me some real-time traffic information. But sometimes how it'll say it'll be similar amount of time if you get off. Let's say I'm heading over to Tosa or something. And I'm heading south on 43, and the way it wants to take me is 43 to 94. But it says it's a similar time to get off at Brown Deer Road and head west that way. Should I get off at Brown Deer Road or not? What do you think and why? So it's telling me I'm 22 minutes away and I'm around Brown Deer Road heading south on 43. And I'm ultimately going to 43 over to 94. And, it's during a rush hour-ish type time. And my GPS says that it still wants me on 43 because it thinks that's the fastest route, but it tells me that if I exit at Brown Deer, it's a similar amount of time. What would you do? Exit or stay on 43? Okay. Why? You would exit? Okay. So what are some this is good. What are some reasons to stay on 43?
I guess it would depend on what you're saying. You have Google Maps up or whatever.
Mm-hmm.
If there's an accidents can clear and then it'll end up being faster.
Okay. Accidents can also happen.
You're right.
So it's really a coin flip, right? Because the slowdown, you don't know if you're experiencing the end of the slowdown or the beginning of the slowdown or the calm before the storm. Right? This might not even be an accident yet. Now, generally speaking, during rush hour, do you think there's a higher chance of an accident causing traffic slowdown on the interstate or on a road like Brown Deer? I don't know even what we'd call that. A medium speed road? Which is going to have, what do you think? It could. But do you think there's are you taking more risk of there being a potential accident in your path, staying on 43, taking 94, than if you get off on Brown Deer?
I would say Brown Deer has more accidents.
Yeah, I would too.
Okay.
If it was a different side road, would you say here's a just
Yeah.
I think it's Brown Deer
It's all the
specifically. Brown Deer is sketchy.
Honestly, there's a higher
All the
probability
stopping
on the
bullets.
interstate just because there's more cars on the interstate. However, to slow you down, it might slow you down more on side roads because they don't get to it as fast as they do on the interstate.
Okay.
Like
There's
the
also
police
more
don't get
people-
to it, and then it could, depending on where it is, you have 3 lanes on an interstate where you can keep moving, and depending on where the accident is on a side road, it could completely block off a road and you'll have to.
Okay. So is it fair to say that we can make arguments on all sides of this and not necessarily know who's right? So we could say that, when there's an accident on the interstate, actually you don't even need an accident on the interstate. Don't you hate when you're backed up in traffic on the interstate and you're waiting till you finally get up to the accident and all it was some cop that pulled somebody over for a speeding ticket, just everybody slows down.
Yeah,
Or there's nothing at all.
Yeah, they're just cop watching.
so bad in Wisconsin.
I mean, these are things, right? And you don't know. So we make these decisions based on the information we have available to us. Usually, so going back to the question I asked, I would usually get off at Brown Deer instead of take the risk during a rush hour time of 43.94 because I feel like even if there is an accident or something like that, I think it's going to be less impactful on Brown Deer because you always have options. If Brown Deer slows down, I could turn right on one of those zinging roads and then just jog past where the slowdown is and get back on Brown Deer or get back on one of the other relatively fast east-west roads. Where on the interstate, sometimes you get stuck, right?
I also deal with less morons. Even just coming here today, I had someone that was literally not even a
half a foot away from the back of my car, and it was like a standstill.
This is on
43.
43? Okay.
It's so annoying.
But you're just guessing that there's more idiots on 43 than maybe there's
Just
maybe the
my
percentage of
experience.
idiots is the same. Maybe it's even better.
Well, my dad always told me everyone who drives is a moron.
Well, that might be true.
Even
Yeah.
I have a point. I think everyone, at the beginning, we already see the GPS said this amount of time is similar, no matter you take on the route. My experience of when GPS telling you taking a route, unless it's forcing you taking a route, it's already taken in consideration in average, at your point and when the accident, you are going past the accident. So it's already taken in consideration. There is accident there, but maybe the accident just happened, or maybe it's already in the middle.
Yep.
I think the GPS already taken that into account. And also my experience is normally the SAS it will slow amount of minutes. My experience told me, or you can say past the data told me the estimation is correct. So my argument is yes, you can go down, but technically when you go down, you also slow down because you're not driving as fast on the highway, and perhaps it's also not the shortest way.
Mm-hmm.
So I think it's all about human feeling in this situation, because if we take the consideration the GPS estimation is correct. If
Okay.
it's wrong, then you have to using your own brand GPS, which is the best way. But if we have the assumption the GPS is correct, and it tells you the same time, it's only about your feeling. It's not really about the act.
Okay, so this comes down to trusting the tool. So is GPS, is that a data science tool?
I think it has it behind.
Yeah, there's a data science behind it, right? Now, it's also a fixed programming tool that, hey, look, this road's here every single day. This is where it's at. And if you want to go from here to here, here's the road you have to take. You got a couple of options. Sometimes you don't have options. Sometimes it's going to say, well, if you want to go this way, you're going to have to get your car on a boat and go across this thing or whatever, so maybe that's not the best way, or if you want to avoid tolls, things like that. But we rely more and more on real-time data, and that's effectively decisions that we're making based on data science, right? Google Maps could be that tool. What about the Weather Channel? When we watch the Weather Channel, are these guys telling us factual data? Or are they giving us predictions based on data? Because we always say, oh, the weather's always wrong. Whatever they say it's going to do the opposite. Right? Yeah, Grandma's always right. She's out there sniffing the dirt. Right. Man, it's going to rain. There's not a cloud in the sky. We better get inside. All right, so.
Irish already knows if it's gonna be a dry year or not.
The whole year. Sometimes it's scary, right? But we don't know. And I always found it fascinating with hurricanes and stuff. We're talking, an hour before the thing makes landfall, and they don't know where it's hitting. Just a little tiny nudge, one direction or another. It might, go one direction, might go another. Could completely destroy one town, might completely miss the coast, even when it's very close. So, huh?
Wind is unpredictable.
Correct. And how it impacts large moving bodies like that are not solid
I think
is also unpredictable.
I think this summer there is a very huge hurricane, right? People is scientists and experts try to predict
Yeah.
the landing on the East Coast, how much disaster would be, but eventually it didn't hitting the coast.
Yeah, a couple different ones, and some of them had it just going right across Florida.
No,
And
I say this year there's a really huge one.
yeah, that's what I'm talking about. Yeah, so some of the models had it going across Florida into the Gulf. Other ones had it going into Florida and basically going straight up. Other ones had it going towards Florida and kind of skirting the coast and hitting the Carolinas and Georgia. It did end up hitting the coast, but it
But
didn't get
not
inland.
at all.
Yeah, well, I'm probably some of the coastal people disagreed with that,
Well,
but yeah,
they will, but not-
it ended up not hitting as much land as they expected. Just
Yeah.
the way the way it went down. All right, so when we use data science tools, you mentioned forecasts and predictions. These aren't necessarily giving us factual information. It's giving us data that we can make decisions based off of, and we hope that this data is, as accurate as grandma might be, maybe more than sniffing dirt. As accurate as your experience driving through Chicago 5 times, maybe that's not a big enough data set to really make those decisions, right? Plus, as individuals, we have all sorts of other variables that you throw into the equation. Some people don't like driving in heavy traffic. They'll take the thing that takes 20 minutes longer just to have a less stressful drive. That's a perfectly reasonable thing to do, right? These are decisions you're making when your goal might be a little different than somebody else's goal. One person's goal might be to get there the quickest. Another person's goal is to get there, safely. I think probably everybody's is safely, just maybe we don't always take that into as much consideration as we probably should. But, whatever. So sometimes our goals are different and we need to make decisions based on that data. What's an example of a decision you might make that is not necessarily a data science-based decision? Let's just take today. Did you make any decisions today that maybe wasn't we could almost call anything a prediction, right? But are there ever times that you will make a decision to do something and you're just positive it's the right decision? So when you left the house today, how many of you put a coat on? Why? It's Wisconsin. Like, I wear a coat in July. Now, did you really need to gather a whole bunch of information about whether a coat was needed today? How many of you actually looked at the temperature outside before you came outside today? Okay, a couple people. Did you have to look at the temperature? If I had asked you, if I had said, you're not allowed to check the weather, do you need a coat today? What would you have said?
I would check the weather anyway.
You're not allowed to.
I would take the jacket.
Yeah, why?
Because I know it's gonna be cold.
Why is it going to be cold?
Because
Because it's Wisconsin, because it's December. All these things add up to, you don't need a whole lot of data to make this decision, right? Even a warm day in December is pretty likely going to still
cold, yeah.
be cold. A coat is probably, at worst, a good idea. Right? This makes some sense? All right, so is that a data science type decision?
Well,
Is it really?
we will have some seasonal data,
Mm-hmm.
to kind of analyze past data, but we don't actually need any calculation for prediction.
Right. We just know, right? The data is relatively insignificant. Or if I say next December, what's today? December 5th? December 5th. December 5th, 2020, you going to need a coat? December 5th, 2027, going to need a coat? Probably. Yeah, but one of the things of global warming is it also have a cooling effect. Doesn't mean it's always getting warmer.
Maybe I'll need 2 coats.
Maybe you'll need 2 coats, right? Okay.
I have an example. So we all know that pi is an infinitive number, and we have algorithm to get the
To calculate the exact value of pi
at least
and there's like a world record for the number of digits it's been calculated
And
to.
if you see the data science and in our technical data,
Yeah, they do an estimation,
calculations there.
right?
So I guess our life is in between normally. So for doing something, most of the thing, or at least a lot of things, we can do very accurate because we have theories, we have science, we have everything behind. But a lot of times we don't really take that into account. We're just using the formal data as so-called experience
Mhm.
to handle. I would say like for do I need to learn code today? I have two ways. First of all, based on experience and based on everything. That's data science. Like I have lived for I have lived for 30 years, and I have so many years of experience of winter, and also know the temperature doesn't really shifting that much in winter because it's already too cold.
Mhm.
And we are in the inland. There's no special thing. So I guess it will be like 99% it will be cold. But of course, I can do a different way. Is like maybe we can create a model and
Yeah.
just
So you could go through the paces of trying to prove to yourself that you're right.
Yeah.
You could apply the tool. Now, one interesting thing I'll go off of just for a second. I'm staying on data science, but switching gears a little bit because I do find it kind of fascinating. So in the book, I don't remember which chapter it is, but they do estimation for pi is one of the things they estimate, right?
Yeah.
3.14159, whatever, blah, blah, blah. So the idea is that we should be able to, through patterns, come up with a value that's roughly pi, right? Now, how did they do that estimation? This is kind of a chicken or the egg type of problem. They came up with, so we have some truths in life, right? So pi is part of a whole lot of mathematical formulas, correct? So in order to estimate the value of pi, they started with a starting point of this is what pi is definitely part of, where pi is the variable in that case, right? So they say, we don't know the value of pi. You know, whenever you're slacking, the noises come through my thing. So, so somebody's probably messaging here, and I see giggles in the audience. So we're treating, in that example, pi as the variable that we want to know, that kind of solve for pi or solve for x. And we're operating off some formula where we know pi is involved. You know, we say, pi r squared, something like that. You have some circle and you have a whole bunch of different circles, for example, right? And r is the radius of that circle. So you have a whole bunch of different, data points for circles. And you happen to have the various radii for 5,000 different circles. And then you can use that to estimate what pi is based on knowing what the radius is. Something like that, if you have some information about that circle. Does that make some sense? So you're actually solving for the variable that is pi. Isn't it kind of fascinating, from like almost a chicken or the egg problem, that we are using known uses of pi to estimate pi?
Yeah, it is fascinating.
Like, how did we know that pi is the required variable there if we didn't know what the value of pi was? We have a formula that involves pi, and we know it involves pi, and we can use that to determine an estimated value for pi. Why do we know it involves pi? I just kind of always found that almost like a evidence of creation, maybe. Something like that, along with Fibonacci type stuff. There's these numeric patterns that just don't seem like accidents. I just thought that's interesting that the way we estimate data for things like that. I mean, there's kind of that category of just, the number 7 is always 7. What do all the alien movies do? They always, the universal language is math, something like that. These are things that human beings didn't invent. It just is. We gave a name to it, but it just is, right? That constant. 3.14 blah 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 value is doesn't matter where you are, where you're from. That value means something, and what you call it is insignificant. So when you mentioned the pi thing, I just thought that was an interesting thing to bring up. But in any case, what you're saying is there's kind of this halvesy thing, right? There's some things where we need to do forecasts or predictions that you really need the data. We don't have a context for this, right? You're trying to forecast what your budget needs to be for next year based on the budget for the last 10 years. And maybe that's not something you just readily have available in your head. That's not data that you either have access to on the fly, or it's too much data that has too many variables to it that you really do need to do an analysis of the data, right? Okay. Then we have the, maybe something in the middle. It's like, hey, should I wear a coat today? I mean, we could go through the motions of collecting data over the last 100 years from all sorts of, points at the same latitude or longitude or something like that, and come up with what is likely going to be the average temperature and the wind and things like that on a certain day. This is all data that we could do and could come up with a number, but we're already pretty confident that if I went through that whole effort, I'm probably going to end up with a value that means put a coat on, right? So we didn't really need the data science tool for that, because we kind of acted as our own little, what is it, the guesstimate? We made our own little guesstimate. So we'll call that a halvesy thing. Now let's say that I gave you a piece of paper and had a bunch of numbers written on it. And I asked you how many 7s were on that piece of paper. Do you need a data science tool for that? What do you need? Definitely not Mr. Gonzalez. Unless there's a very few number of 7s, he's capping out at 2. Okay, so it's a fixed number of things, right? You're going through and you're just counting the number of things that are there. Will you always get the same answer? If I give you that same piece of paper and we're assuming you're counting accurately, you'll always get that same answer, correct? There's no prediction. Even if you will, and there really isn't a such thing as taking a random sampling when you want to take into consideration the entire data set in front of you. So would you say that counting the number of things that exists in a data set is a good use of a data science tool? It's like using a power tool to solve a problem that is really fairly trivial, right?
What if it was like a really big data set though?
Well, even then, would you use a data science tool? Would you write a program that just reads in the file and has a little counter, and every single time you say, if char at is equal to 7, count plus plus. So now you have a program that just does the counting. And that's not having to use any, visualizations or, fancy data splitting stuff or bringing things into data frame, data structures, none of that stuff, right? Just like, I'm just going to look at the characters and I'm going to count them. So that's not the right tool or that's not the right kind of problem that data science benefits us. Because, you mentioned that predictions and forecasts are something that data science might help us with. And some of these things come in some different forms, and some of them are maybe harder or easier to make depending on what the data looks like. And, one of the things we're going to talk about today is machine learning stuff and artificial intelligence, which I think kind of pulls us back towards maybe more traditional computer science stuff. But sometimes we just suspect there's going to be a pattern. And we might look and not find a pattern, correct? So, for instance, if I say it's December 5th, do you need a coat today? Well, it's going to depend on context. If you're in Wisconsin, the answer is probably yes. But what if I ask the question, it's December 5th, are you going to need a coat at every point in the world, no matter where you are in the world? Some places it might be a really bad idea to have a coat. Like today, where might it be a really bad idea to have a coat on? Huh? Australia? Because when it's our winter, what is it there? It's their summer.
Is it over 100 degrees?
Yeah, so southern hemisphere, especially when you get pretty, deep in the southern hemisphere, when it's really cold here, it's probably really hot there. Make sense?
One place, one code might not be enough.
Right. Yeah, you go pretty north. You know, what about July 17th? Do we need a code here on July 17th? Probably not. Do we need a code? Do we need a code on July 17th at the North Pole?
You
Probably.
always need-
Yeah, probably always going to need that coat, right? Even with global warming. What's this?
Gonzalez wear a coat.
He does actually have. Well, he doesn't have. He does have a coat.
Would he get a North Pole?
He always wears He wears sweaters. What is he going to wear in this cruise if we even go? Is she going to let him on the cruise? I didn't even consider that. I don't know if we can travel with that, Mr. Gonzalez. Okay, so that might be something that we do need a data set for if we're not necessarily sure where we would need a coat and where we wouldn't need a coat. At what temperature do you start wearing a coat? Each of us are going to kind of have our own comfort level, right? You know, for my wife, if it's south of 70, coats are coming on, right? She is always cold. You know, for me, the coat comes on when it's below freezing, maybe something like that. Maybe mid 40s. I might consider a light jacket, something like that. I got quite a bit of insulation I'm bringing with me all the time anyways. But, you know, the idea is we all have our tolerances, but we could take our tolerances as an individual and plot it across any point on Earth and decide whether or not we could define our own threshold, right? For each of us, we can kind of say, well, I will put a coat on if these conditions are met. You know, and it's probably going to be some combination between temperature and wind, right? And maybe throwing in how sunny it is. Sometimes you can have a day when it's 50 degrees and windy and it feels colder than a day when it's 30 degrees and sunny and no wind.
How long you are going to walking outside?
Could be. So we have some variables, but most of us probably feel comfortable or confident that we could come up with a fairly quick algorithm for whether or not we're going to need a coat given 2 or 3 inputs, right? We can make that work. That's not a decision that on a daily basis we're making. It's not taking us 45 minutes to decide whether to put a coat on. It's a quick little mental check-in. Or, as she pointed out, if you're in Wisconsin, you just grab your coat. I keep an extra coat in the car in case I almost don't survive the trip to the car wearing the coat. All right, so we could all do that. So now it might be interesting to visualize you at different points on Earth wearing coats at different points in time. You know, where is the crossover in the seasons? You know, so whenever you're, when we travel, we might say, what's the weather going to be like there then? How am I going to pack? You know, because your personal threshold might be interesting. Your personal threshold gives the starting point information for what kind of clothing you might wear at a particular location at a particular time, based on historical trends, right? So if I'm traveling to Sydney, Australia in August, I can't go to the Weather Channel right now and get a great idea of what the weather is going to be like in August. They're not forecasting that far out. I can go and look at what it was last August. I can look at, some historical data and find out what is it roughly like in August there. But at the end of the day, I could probably come up to some sort of idea that it's going to be one of the cooler seasons there in August, right? Now, if I want to visualize where I want to travel in August, I might start off by saying, I want to go someplace where I can wear shorts, or I want to go someplace where I don't have to wear a coat. And my vacation is during this month or this 2-week period, something like that. So now given a data set of weather, could be historical data, could just be last year's data, will at least give you a decent snapshot, you could effectively plot your threshold across the planet and find out where are viable places for you to travel during that certain period of time, given the types of clothing you would like to wear on your vacation. That make sense? So that's the kind of question that a data science approach and a visualization helps us answer. Does that make sense? It allows us to visualize something that's harder for us to conceive of in our head. Because if I just ask you that question right now, if I say, okay, let's say you want to go somewhere in August where you can wear shorts and you don't need a coat. Now, most of us could start coming up with, a handful of options based on places we have been, parts of the country we've been in, parts of the world we've been in, but we're still going to be limiting ourselves. Do any of us know? I don't know that I'm the most traveled in the room, but I'm guessing I am. So, do I know every single place where I could go and wear shorts in August? Well, I could make some decent guesses, but there's going to be places I've even heard of. Right? You just kind of make that's probably one of those islands out over there somewhere, something like that. But it might be interesting to visualize that and maybe see it, either plotted, maybe even overlaid on, a map. Where can I, based on my thresholds, wear shorts in August? Something like that. Because it actually might go both directions, right? You might have some sort of maximum temperature. So as a golfer, the cheapest, where's a good place to golf in August, let's say? Wisconsin's a great place to golf in August. Where's a horrible place to golf in August? What about Phoenix, Arizona? Would you go golfing in Phoenix, Arizona in August?
I wouldn't go to Phoenix, Arizona.
Yeah. Courses are open. But they're dirt cheap. They are dirt cheap. Same with Florida. Florida's among the golf capitals of the world, right? You want to go and play the really fancy courses really, really cheap? Go play them in July. Go play them in August. What's the weather like in Florida in July and August? Yeah, 90 degrees, 190% humidity. It's possible in Florida, trust me. Okay, but it's accurate. Okay, you're outside for 5 seconds in Florida and you've sweated through your clothes. It's that humid there. Phoenix, they don't have the humidity. They just make up for it with ridiculous heat. It's 113 degrees. So you have to just basically just drink water constantly. It's so hot you don't sweat. Your body isn't even capable of cooling itself down. But golf is cheap. So depends what your goal is. You could pay top dollar for golf here in Wisconsin in August. Okay? These are the types of questions that can be answered on a more global level with data science tools. Because as an individual human being, we don't have all that information available to us. And as data sets get bigger and bigger and bigger, we start losing track of the commonalities, right? Similarly, we talked about traffic earlier. When would be the best time to, when might rush hour happen in Rome, Italy?
We don't know.
Yeah, we maybe have some suspicions, right? Jordan mentioned earlier that, okay, well, we got some common patterns of when people go to work and when people leave work, right? But there's kind of the American version of a workday, right? Could be. But other countries have different patterns, right?
I was actually there last summer. They stopped working at 3, so the rush hours are longer.
Yeah. So, and that's just one example of another country. But we have other cultures all over the world. You go to India. When's the best time to avoid traffic?
No.
Yeah, there's no time. You can't avoid traffic in India. That doesn't exist. It's not a thing. Although you come from a place that's a little bit less traffic than Hyderabad, because he's west coast. But yeah, I've never seen traffic like Hyderabad, India. It was ridiculous. I've never seen it. 3 a.m. there's traffic. Just stop and go. just wall the way as a parking lot at 3 a.m. I've never seen anything like it. Yet I was there for 2 weeks and didn't see one accident.
What?
Not one.
What's causing the traffic? Just masses of people?
Well, I mean, India is fascinating. I mean, because you have, the most populous country in the world is China. The second most populous is India, and it's not far behind. And India is supposed to overtake China here in the next 10 years. But China is almost 3 times the size of India. So they're kind of close in population, yet India is way smaller. So those people are compressed into this it's ridiculous. I've never seen anything like it. To the point it's fascinating. It's just absolutely fascinating to see that many people. And in cars, they have a language with honks and stuff. They're talking to each other through the
In Haiti, it's kind of the same. You don't understand, you can understand what's going on, but the traffic is horrible. They horn to each other and they let one go and then other go.
Yeah, they kind of figure it out.
Yeah, I don't know how it works.
But I mean, it's the only place where I've seen the southbound traffic be too slow, so the people that were really going to rush just went southbound on the northbound. Nobody seemed to care.
Well, the police?
Oh, there's no police. What are they going to do? They're stuck in traffic too.
They would never be able to get to an accident there.
Yeah, I mean, and sometimes you have entire lanes just blocked by a cow.
Oh, that's where the traffic comes from. It's not the accidents, it's the cattle.
I would say cows were not a problem. Dogs were a problem. There are a lot of dogs.
Cause the traffic.
Yeah, but I think they would hit a dog. They're not going to slow down for a dog, but they'll go around a cow. Yeah, it was a pretty interesting place. But punchline is we can't necessarily take our cultural data that's in our head here based on our experience with Chicago and Milwaukee and the average American workday and stuff like that, and take it immediately to another place and start making decisions that we can rely on, right? So when you're on vacation, sometimes things that you would take for granted back home are no longer truths on vacation. That makes sense? These are the types of things that data science helps us answer. So what I found interesting with a lot of the assessments, with the questions that as a group we've been coming up with, so many of them are about how many of something, or counting the number of things like this. And it's not that that's bad, because you're still getting to practice with the tools, right? So it's not a waste of time, because maybe you even might say that it's more instructive to ask an easy question that you can answer using the tools, and then you have the tool giving you the answer that you were expecting, right? And there's some value in that. It's like, look, this isn't all that interesting of a question, but I know the answer should be 32. Therefore, I'm going to run this on this uninteresting question, and I get the answer 32, and now I know I wrote that code right, I'm using the data set right, my visualization made sense. I didn't need to go through all those hoops just to answer that question, but I got the right answer. So there's an academic, instructive aspect of it. But those questions are not interesting questions. Does that make sense? Okay, so let me take a... Do I want to... Let me introduce for a few minutes the machine learning stuff, because it's going to be related to your final.
When is the final?
Huh? Right now.
Listen up. You're gonna listen to this portion and you're gonna do the final. Calm down.
This is going to be data science. Okay, so I'm going to be grading this in real time, so the number of drinks that get around. So what all do we have back there? Things like Maddie just relocates. like, look, I'm just gonna settle in. All right. What was I talking about? Oh, so everything in the book so far, our second half, has kind of been talking about different ways of visualizing data. These last couple chapters have kind of been talking more about estimating numbers, or estimating things, let's say, which I actually find maybe that could be a harder thing to come up with interesting problems for. I think that the problems that you can find related to estimations are interesting, but it might be harder to come up with interesting things to estimate. I don't know, something like that. Or at the very least, you have less confidence in them. Estimating pi, again, we know what the answer is supposed to be, right? But if we're trying to estimate what next year's revenue would be for a company, we're solving some weird economics function for some variable that we are, bringing into question, we don't necessarily know if we have the right answer. We have to wait to find out if we had the right answer, we had the right estimate, something like that, right? So I think those are sometimes harder questions, but it's also what we rely on data science for, because making that estimate for next year's revenue, next year's profit, whatever, we're probably going to get, as long as we're bringing the right variables and enough data into the situation, we're probably going to get a more accurate answer doing that than if one of us just kind of blurts out a number, just our gut feeling. Like, how much money is Apple going to make next year? Gut feeling is going to be a lot. Okay, then you got to decide, well, what does a lot mean? Okay, what does that number actually mean? And we would make a guess, and it's going to be all over the place, and it's all probably not going to be enough, right? Something in the billions is what they're going to make. Profit will be in the billions, revenue will be in the higher billions, but they'll make a lot of money. So any one of us coming up with some sort of prediction for Apple and just saying they're going to make a lot of money, that's not necessarily a useful piece of data for them, right? Because who cares about the amount of profit Apple's going to make next year? They're shareholders. Apple's a publicly traded company, and the value of one share of Apple is mostly directly related to the profit Apple made. Does that make sense? It's really interesting. So this laptop, even though I have my volume off, the HDMI still comes through the thing. Yeah, it's strange. So, oh, it's terrifying?
It was the volume from the Ann Arbor guy in Wall's class.
Okay.
Normally it just comes out of his laptop, but he hooked it up here, so all of a sudden, just in the middle of class, it just boomed to everyone. And he dropped something and did something else, and it was just terrifying.
Oh. I thought you were talking, wasn't there some, this was unrelated, but wasn't there some word that somebody Googled in that class not that long ago he made up that wasn't a made up word? Yeah. Yeah, so we're not going to Google that in here. But,
Don't Google it.
Don't. I actually think the word is a Googleize.
Yeah.
It's Googleize. Don't Google eyes.
You can.
Huh?
They're kind of pictures involved.
Well, I get it, but I'm not doing it on recording. It's right there on the screen. Yeah, don't Google that. Well, Google it later. Yeah, well, that's the first thing that comes up when you Google it. Don't do that right now. We could do it later. All right, so let's talk about machine learning stuff. All right, so when you hear artificial intelligence, you hear machine learning, what do these things mean to you? And how does it relate to data science? Because we have not read that chapter yet. That's correct? whatever chapter that is, the machine learning 14 or something, 27?
It's either 16 or 17.
The only chapters we didn't read was the data mining and ethics.
17 is ethics.
Oh, we're not reading that.
16.
We're not reading ethics. Come on.
Yeah, data mining and ethics.
All right. So it's the data mining one. So we haven't read that one yet, right? Good. All right. So because that's what the final is going to be about. So isn't that good? I've zeroed it in on a single topic.
One lecture.
Well, no, I'm not even going to fully lecture about it. I'm going to just introduce it.
Cool. Even better.
Yeah, this is great. This is perfect. All right, so what is artificial intelligence? What does that mean to you? Broad strokes. What is AI in general?
Using machines to simulate brains.
Computers acting smart,
Yeah, no, that's a better way to say it.
right? A human being's version of what is smart. So if you can have a computer that's roughly acting like a human being, where human beings have this giant scale of smart to not so smart, right? But we would still call all those people humans. If we can get an AI to roughly act somewhere along that spectrum, we would decide, that's artificial intelligence. It is intelligence that is artificial. And when we're thinking about that, the things that we create that are artificial are going to be computer programs, maybe attached to a robot, something like that. The robot makes it look like a person, look like a living thing, and the computer program makes it, quote, think like a living thing. Make sense? All right.
Test.
Huh? Oh, Turing Test? Yeah, Turing Test says that if you can be talking to a computer program and not be able to distinguish between man or machine, then that's AI. It's considered to be, it's past the test for artificial intelligence. It's called the Turing Test. All right, so that's what AI is. Now, related to this is this idea called machine learning. Okay, what is learning? Just in general. We all know how to learn stuff. We spend our whole life learning things. What does it mean to learn things?
Be good at it.
Acquire knowledge. You can learn something and suck at it,
It means
right?
you failed learning it.
I mean, I've watched a whole lot of sports and I'm not very good at. I could tell you a whole lot of stuff about a whole lot of sports. Some of those things I'm not skilled.
But I
So
think-
skill is different than learning.
But I think learning at least right learning you need to get a positive outcome. Right?
Okay, so somewhere in there we do have an idea of correctness, right? So somebody, even if you're not very good at, say, a sport, you can learn the correct technique for something, and even if you can't necessarily perform it at a high skill, you know what's correct and you know what's incorrect.
Yeah.
You have an academic knowledge of it. So learning is absorbing information and retaining it, problem solving with it, whatever, right? But it's the act of us taking something that we don't know or are in the process of knowing and building it up. Okay? What's a machine? Computer thingy, right? So what would machine learning be? A computer thingy learning like a person. So a computer acquiring knowledge in a similar way to how a human does. Whatever, something like that. How do we learn?
Practice,
Repetition.
recognizing.
I mean, aren't there different learning styles?
Yes.
There are a lot.
How many of you learn well from watching videos? Some people do. How many people learn well from reading a book? How many people specifically don't learn well from watching a video? A lot of people struggle with sitting there and watching a video and, unless you get skilled at the whole pause, copy what's on there, do it a little bit, then go back and unpause, you almost have to force the video to almost act like a book, right? You just you're taking little hops forward or something like that. I tend to like learning from videos, but I won't necessarily do stuff while the video's playing. I'll go through the video and get the overarching concept, and if there's aspects I want to go try on my own, I'll go and do that. Because then you're getting it, you're just getting the data dump of it, and then you're deciding, is that something that I'm interested in doing or something that I just want to throw into the brain as, a knowledge store of this exists. Something along those lines. Okay, but it's fair to say that different people have different learning modes, and if we spent some time, we probably could come up with some sort of reasonably relevant list of different ways that the average college student learns. Fair enough, or average human learns. All right. Now, with artificial intelligence, we generally break this down into a couple of broad categories, and that's supervised versus unsupervised learning. So what would unsupervised learning be? What does supervised mean?
You check the outcome is correct or not.
Okay. So in general, if somebody needs adult supervision, that means you need a person there to watch over you because you're not trusted to take care of yourself, right? So, a 3-year-old or Mr. Gonzalez needs to have adult supervision, otherwise bad things happen, all right? So it would be a bad idea for him to be unsupervised. So unsupervised learning says we're going to put this potential AI there and expose it to information and let it learn somehow, not necessarily giving it feedback of right or wrong. Does that make sense? And so that's, would you say that that's a great way of learning for a human being normally?
Not efficient.
Yeah. Could be a way of learning some things, right? But generally speaking, it's not, when we think about learning as a person, we're typically not, that's not a mode of learning that most of us would be comfortable with, correct? So, doesn't require feedback. Not really human-like. Supervised learning. This is the one that we like. We like to have the answer, right? And then we make adjustments based on that answer. But how do we make adjustments? So this kind of goes back to this idea of how do you, what's the purpose of a computer? What's the purpose of a programming language? These things help human beings solve problems using a computer in a way that's similar to the way that we solve problems in real life. Okay, so if you are learning your 1 through 5's multiplication table, and I say, what is 5 times 2? And you say 9. So you give me the wrong answer. And I say, that's wrong. How do you modify yourself so that you'll be less wrong next time? What does a human being do? Can you even articulate that?
Write it 10 times.
Okay. So I say 5 times 2. You say 9. I said, the answer is actually 10. Maybe through repetition, you go and say 5 times 2 equals 10. 5 times 2 equals 10. 5 times 2 equals 10. Kind of you drill it in there and hopefully it sticks. Okay? But do you actually know what's happening inside your head when you're writing it multiple times? Something is updating, right?
Yeah.
Somehow you're reinforcing this knowledge that's inside your head. Maybe a generic way of putting this is that supervised learning is a guess based on the current version of the model that is either right or wrong. I'm going to put in parentheses here, or some degree right or wrong that dictates a tweak. It's called a potential tweak. In future guesses. Now, I said the word guess here. So when I asked you 5 times 2, everybody in here, we know 5 times 2 is 10?
9.
It's 9. See? Supervised learning. Teacher said it's 9. It's 9. That's what we're putting on the test. Anyway, you got it. That's the whole exam. The whole exam will be 5 times 2 question mark. And then you get to decide what answer I'm looking for. Oh, that would be a pretty good one. Am I looking for the right answer? Or am I looking for the 9?
That's really tricky.
That would just be a fun test. Just watch you all stress about it.
I will get 50-50.
You flip a coin?
No, half of the test 9, half of the test 10.
No, but there's only one question.
Oh, I thought you said it.
One question on the test, graded in binary, all or nothing. 5 times 2.
Would you take the 50% though, or would you rather shoot for 100?
So are you asking, like, is there, if you had the opportunity to, like, take a 50% on the test and not have to fill it out?
No, what she's saying is that you're guaranteed 50%. If, let's say there's 10 questions and every question is the same and it's either one answer or the other, she did half one, half the other. That's a guaranteed 50%.
Oh, okay, I got you.
Or are you like doing where you would?
So that's only a D, right?
50-50.
So you would just accept a 50% on it?
I'm a conservative person.
That's not even conservative, it's still an F.
I mean, for investments and conservative, so this is a conservative investment.
But you
I
get
will
nothing
notice
from
it's
that.
better to
Well,
50 than
you get 50%, you get more than nothing, you just are guaranteed not to get everything.
But in the investment, like in the world, if you don't gain anything, it's like a bad investment.
When I say guess, I say 5 times 2. We all know that 5 times 2 is 10. But do you really know, or are you guessing?
I think
Are you confident that 5 times 2 is 10?
Yes.
Why?
Well, that's what we've been
we
told.
should really ask you: is your 5 times to
Given the
10 or like
definition
is
of multiplication.
Really?
Yeah.
Tell me about that. What's the definition of multiplication?
You take, you have 5 things twice,
Yeah.
and then you count these.
You what, add them together?
Yeah.
Okay, and you're sure that's 10?
Yeah,
Why is that 10?
because that's how our number system works.
Does it?
Yeah,
How do you know?
that's how it works. We're a decimal-based time system.
Okay. So at some point, was there a pattern that you had to learn for how our number system works? You know, we dealt this earlier in the semester with binary and octal and all these things where number systems all work the same with different bases. But there is an underlying pattern that we did learn. So when I say 5 times 2, are you actually thinking about, okay, well, I have 5, and I have it 2 times, and I add those together and I get 10. Is that the process you go through?
Not anymore,
Why?
because I learned it.
Okay, so what's the process you go through then?
What that is, that's how you teach kids.
Oh, okay, but I'm asking you, your process. So I asked you 5 times 2, and you're confident you would come up with 10. You're not just cheating off the rest of us?
Yeah.
You come up with the 10. Okay, so how? How did you come up with that 10? Where did you search for it?
Because you remembered it.
You remembered it. So you just memorized all the math?
At some
We
point,
had to.
you
I
memorize
think it's
them. At
the
some
single
point.
digit.
Your times table, up to 12.
Okay. What if I gave you a bigger number? 713 times 27.
Then you would go back to that process Like at the
And that's
beginning,
what
the
you did
whole
before
5
to me.
plus 5, or twice, right?
Oh, so you change tactics.
You-
So multiplication is, so 5 times 2
Mhm.
is something that you just know.
That you could just remember.
You're not doing math to get you 5 times 2, right? It's a targeted guess. It's a practiced
I think
guess.
it's more like it's a cache.
Cached memory, okay, well, that's fine. But we just know it. But it's still multiplication, right? But if I give you something more complex that you didn't just happen to memorize, because there's an infinite number of numbers, you would have to then revert back to a generic pattern that you have memorized. This is how I perform the act of multiplication given these inputs. That make sense? Okay. Now, would you agree that there is an underlying pattern to multiplication?
Yeah.
We don't necessarily think about it in terms of a pattern, but we do have an underlying pattern of multiplication. And we happen to be able to prove that to ourselves when we happen to say 5 times 2 is 10 and we're convinced that we're right. And then we have this, this formula that we can use every single time we want to do more complex multiplication. We can throw that formula in front of us and we can just follow the rules and come up with a number, and that number is right. So that we have this algorithm that captures the pattern of multiplication. Fair enough? Okay? And we've decided as human beings, given the constraint of our memory, we can only store so many hard-coded values. Unicode, something like that, right? We remembered a subset of some of the math problems, some of the quick numbers we might need to use on a daily basis. And if you're in a specific job where you might deal with some weird numbers that the average person might not know, you're going to have some other things you've memorized, right? Maybe some sort of weird lookup code at your work that makes no sense to another human being, but you've just typed it in so many times you just know it, right? That kind of stuff. So we have our memory. Maybe it's like cache that we rely on. But other than that, we have this idea of stumbling upon patterns, learning patterns. Somebody had to teach us multiplication. Some human being figured out multiplication, right? Do we know, math major? Who invented multiplication?
Do we know math major?
Oh, she was bragging about the math major thing. Who invented multiplication?
That's one Google story.
Just Googleize that. Go on. You're going to want to Googleize that.
Has a math major, you don't have.
So,
The Babylonians.
is that the Babylonians? Intriguing. Tell me more. We're just reading Wikipedia at this point.
4,000 years ago in the Babylonians.
All right, I've stopped caring. All right. Okay. Some human being figured out math. Now, did multiplication exist before that?
For sure.
Yeah, it existed, right? But some human being stumbled upon the algorithm for how to do multiplication. Now, how many of you think that if somebody hadn't taught you the algorithm of multiplication that you would have stumbled upon it yourself? Why?
Because we're dumb.
Well,
You don't think about that.
I think it's
In
not
basic
that
things,
straightforward
we will figure
enough.
okay.
So I think math is a thinking pattern. Before we get used to the pattern, it's more like if you don't go through the first door, even cannot start it, reaching the next door. Like a multiplication is like a door, like not the first door.
Do you think you need to be very, very, very focused on a problem whose answer you are seeking in order to stumble across, or at least have a real fighting chance at stumbling across the pattern? The person who came up with multiplication, do you think they were really, really, really focused on finding the generalistic way of calculating whatever they called it back then, and they just happened to come across it? like experimental physicists, they come up and they try to answer questions about like black holes and stuff like that. So they have some information they know about the math surrounding that. And then they come up with these hypotheses and then they start testing it and seeing if the math works, right? So maybe somebody was interested enough in some problem that they stumbled into, through trial and error, a pattern, right? Is it also possible that just by sheer coincidence, you kind of like the idea of, somebody plays the lottery, you have one person who buys, 5,000 tickets, doesn't win. One person buys one ticket, does win. That person just stumbled into it where the other person had the deck stacked in their favor, relatively speaking, and wasted money on all those tickets. So either one of those things can happen, but you probably have a better chance of coming up with a solution to a problem that you are actively looking for and working on, correct? Are any of us so focused in on a very, very, very specific topic enough, or so intrigued about finding some answer that we're willing to put everything else kind of on hold in order to seek that truth?
It reminds me of in physics, like the law of gravity. Those are pure guess, but then proved by experiment.
Yeah, or you could just knock an apple off a tree and watch it fall.
I'm saying like it's a the square of the.
I got you. The actual.
That is pure
Right.
guess.
Yeah.
They don't really know, but they feel it might be the answer.
Well, really, they did the human version of estimating it, right? They measured it over and over and over again until they could come up with a generic way of representing it. So, in general, human beings do not have the temperament to stare at an individual problem long enough to stumble across a difficult to find pattern. Somewhere we have that threshold, right? Difficult to find for a human might be difficult to find for a computer might be impossible. Or you have those people that say, well, nothing's impossible. Basically impossible for a human being to stumble upon, especially when we're dealing with large data sets and trying to get stuff out of that. That make some sense? So one of the things that we have, and this is kind of maybe the scary sci-fi thing with AI, is as we get further into approaches to machine learning, models for allowing our computers to process data and search for patterns. Because what we can do is we can have our computer look at a single data set and process through that data set millions and millions and millions of times, searching for that pattern. Can any human being ever do that? That didn't fly, right?
Just like a Deep Blue and AlphaGo, the computer is calculating something.
It can do something we can't do.
Yeah.
God didn't build us that way. We get distracted too easily. All these things. We're good at a lot of stuff. We're way better than computers at a lot of stuff. But that kind of focused thing, computers are very good at. That make sense? Okay, so the idea of machine learning is creating models where we can effectively have a computer, and we're going to focus on the supervised learning side of this, where we can have a computer stumble upon the pattern, the generic pattern for the solution, given just brute force, looking at the problem from every single angle until you finally get it. And the example I usually use is, and it was my first experience with machine learning years ago, was we wrote it was in a data, like an algorithms class, and we created a neural network for, we were representing numbers as binary digits, so it had a whole bunch of different inputs into this neural network. And we would feed it the 1 through 5's multiplication table, and then it would make a guess for the answer. And do you think it was getting a whole lot of them right at the beginning? No, it was getting most of them wrong. So, because it was just guessing. And if I walked up to a 2-year-old and I said, what's 17 times 5, what's the 2-year-old going to say? They can't do math yet, right? Can a 2-year-old do 17 times 5? Can you do 5 times 3?
2-year-olds can't even talk yet.
All right, so no. The answer is no.
You probably can ask him 1 apple and 2 apples, how many apples you have. Multiplication.
Okay, so the answer is no. They can't do math yet. Okay, so I walk up to a 2-year-old, but some of them like know what numbers are. Some, right? So one of them like could maybe say 4. Just a pure guess. Let's say yes. All right. Can they do that at 3?
I would go with 3.
3. Okay, 3-year-old. So 3-year-old, you walk up, you just throw them some math problem that they definitely can't do, but they know enough about numbers that, okay, he's looking for an answer that is a number. So I'm just going to guess a number. Probably going to guess it wrong, right? Okay, so then how do you teach the kid? You smash them, right? And but that's how computers work. What do we do when the neural network guesses and it gets it wrong? We effectively slap it on its wrist, say, no, you're off by this much. Here's this algorithm for you to go back and, rewire yourself to hopefully be off by less next time. And then we feed it the next math problem. Do it again. The next math problem. Update it again. We do that millions and millions and millions and millions of times until you finally have this brain model that has been balanced. All these little connections inside the brain. It's been balanced to be able to get all of the 1 through 5's multiplication table correct. It doesn't know how to do math yet, does it? It's effectively been beat into submission and updated itself enough times that it now is just like perfectly balanced for the 1 through 5's table. That's what you have. You can feed it any input in the 1 through 5's table and it will give you the right output. Then you take it to some data that it's never seen before. And you test it. So you feed it the 6 through 10's table. And it gets them almost all right. This is data it's never seen before. It has stumbled upon the pattern of multiplication. Does that make sense? That's what machine learning is. Now, back when I did it years ago, and even in, today, if you took an artificial intelligence class that was focusing on neural networks or something, you might implement an actual neural network data structure, because that's what it is. It's a data structure. It holds neurons and weights between those neurons and all this other stuff. And what you're actually doing is you're increasing or decreasing the strength between two little neurons. There's like a connecting wire between them. And next time you get this one input, it's going to fire a little bit harder, a little bit weaker, and ultimately you start getting better answers. But now we have tools that have evolved out of the data science tools, and the book introduces some of them, that allows you to take a data set, train it on that data set, and then test it against another data set. Same data, but same type of data, but data it hasn't seen. Does that make sense? All right, so the final exam.
Hello.
We're finally paying attention now, is that it? Is going to be a combination of I would call it a relatively short project, so not a hard data set to train and test, but something that allows you to experience this in real time, along with a series of questions that you'll be answering related to that data set and the results of your training and testing, I guess. So, but it's all going to be on machine learning.
This sounds terrifying.
Yeah, it's going to be great.
How are we gonna even do it?
Yeah, it's going to be great.
What are you gonna use to do it?
You're going to the same stuff you've been using. Yep. Same stuff you've been doing.
With, you're just gonna give us an Excel file and like answer these questions, or?
Yeah, ish. The next chapter in the book gives you sample code for going through. I think they use the tulip stuff for classifying. So instead of solving math, what they do is they say, so maybe here's like a simple example. A simple example might be, let's say that I've given you a big list of numbers, like all the numbers between 1 and 1,000. And I've set each number, there's a column in the data set that says whether or not that number is even or odd. Okay? Now, as a human being, I can give you a number and you can tell me whether that number is even or odd. Can't you? If I say the number 16, even or odd? Even. If I say the number 19, even or odd? How do you know?
Last digits,
Did you actually try to divide it by 2 and see if it had no remainder?
just the last digits.
Right? You've learned the pattern of even versus odd. So if I took that data set and I used the machine learning tools that are built into Python, that you already have, the Seaborn has the stuff built into it, you can train it by feeding it data, having it guess whether that number is even or odd. It then adjusts itself. This is all built into it. It's going to be like 5, 6, 7 lines of code. The tool does it for you. Okay, you're going to be using the tool to do the machine learning. And after you go through some number of iterations, it will be able to take any number, even numbers it hasn't seen before, and tell you whether that number is even or odd. But it's not doing it. It's discovered the pattern of an even number versus an odd number. It is not necessarily, just like we're not necessarily taking the number, dividing it by 2 and looking at the remainder. Yet I could give you any number and you can tell me whether or not number is even or odd. You're looking at the last digit, right? And coming up with some conclusion. If I give you any binary number and ask you if it's even or odd, you look at the very last bit,
It was simple.
right? Same exact thing. But the reality is that the neural network, which you don't have to build a neural network. It's in the tool. The tool has the neural network. You're focusing on the data. So It's in chapter whatever, 16, 17. They give you sample code. You're going to be reading that chapter. It's part of it.
Model prediction.
Oh, which chapter?
No, it wasn't.
Whatever. It's in the book. You'll read that chapter in the book. Trust me. All right.
Are we writing a paper on it?
Well, it's not going to be a paper. Oh, you mean were you writing a paper on the chapter? No. Your proof will be the result of your thing. It's in the machine learning chapter.
This is the machine learning chapter.
All right. So I will have that up. I hope to have it up tomorrow, but it'll definitely be up by early in the day on Saturday. I don't want to promise tomorrow and not deliver. And it's due midnight next Sunday.
And how long are you expecting us to be struggling at getting our heads up to the wall?
60 to 80 hours.
Please just leave like 6 or 8 hours. I would be happy.
It's I would expect after you get the basic thing working, I don't think it should take you more than 4 hours.
Times 3.
No, I've adjusted that for like the pace of that this group has seemed to solve stuff at. It's going to be a very simple problem of just going through and understanding how machine learning works.
Can you give us an example?
I just did.
No, a program example in Python.
Well, I'll take you through the example in the book because I don't have Python installed in this machine.
It's your new computer.
Huh?
It's your new computer.
Well, yeah, right. Correct. It's my new computers. I don't have all the tools and stuff installed in here
Wait, why'd you get a new computer?
because I needed an escape key.
6 months old. Because he closed
I heard
something.
that sassiness.
It's true though.
I have a physical escape key now. It's better. My other laptop didn't have a.
The escape key on the touch bar?
No, I use the escape key all the time. No, I didn't like it on the touch bar.
Actually, no, I don't like mine on the touch bar either.
You have basically a week and a half.
But I'm stuck with mine for 2 years.
So
at least.
basically, alright, so you want Python in chapter 16?
So we have a final project, not a final test.
Ish. I would say it's not a final project. It is a test because the project part of it is going to be very simple.
So there's no conversion problem.
Correct.
Okay.
But what if
Or
it's
is that
not
your
simple?
folks?
It'll be, well, okay, it should be simple. I'm going to walk through this code.
Okay, what is, let's say 6.4? 16.4?
No,
Supervised.
16.4.
Supervised learning.
Yeah, doesn't it say the same thing that the slide says?
Yeah, I have it in my notes.
All right. So you import a bunch of crap. All right, so now here's our data set. And this is the data set that deals with, so one of the things we often do with machine learning is something called classification. So I've given you kind of a cool example, which was my first experience with the multiplication table. We won't do that with it. You could, but effectively what you're doing is you're it's much easier to use these tools for classifying something as into 3, 4, 5, 7 categories, where the answer to a math problem can be an infinite number of categories, right? So you're kind of using the model differently. That's where I use the even and odd one is a little bit, we have 2 classifications. I give you number, you tell me whether it's even or odd. That would be a very simple example of machine learning example. This guy here takes this data set for these irises, this flower, and it has a whole bunch of information. And they've used this iris data set throughout the book several times. We've seen it, right? All right, and it has a whole bunch of piece of information like with petal length and things like that. And based on that data, I don't remember if there's 3 or 4 or 5 different categories, but it tells you what kind of iris flower that is based on those characteristics. Make sense? All right, so this line right here is reading in that data set. We've seen that before. That's not anything strange. All right, then we are tearing past the first couple of values, because it's got the headers in there and stuff like that. So you're just getting to your regular datas. So now we're having our training set, our testing set. So the training set is what we're going to train our neural network on. The testing set is going to be what we are going to then test it on once it's trained. So with our petal information, let's just say we take half the data set. So we're going to train our neural network on the first half of the petal data, the iris data. And then once that's getting us good accuracy, then we'll test that model on the second half of our iris data. And it should be able to classify them with a high accuracy, even though it's data it has not seen before. All right, so we have this function here called train test split. Okay, where we give it a x, which we defined right here, bunch of values, a y, which we defined right here, what our test size is, and I'm guessing what random state is just always going to be 0. I'll have to look at what that function does. But what this guy ultimately will do is he will split this stuff up into 4 data sets. A training data set for the X, so this is a subset of the data containing petal length and sepal length. So that's what X is here. So this is just petal length and sepal length data. And then the second data set has all of your labels. So things we've used for charts and stuff before. All right, so our X training data will come out of that, which will have, like I just used as an example, it might have half of the data on petal length and sepal length. The test data will have the rest of the data, let's say, on petal length and sepal length, along with the category. So that's what these values are. These labels, I don't remember the names of the flowers, but it's here. Oh, is it down here? Yeah, whatever the name of the flowers are. Here, I'm just going to call them A, B, and C. I don't remember what the flowers are. But so the labels here might be A, B, and C. There looks like there's actually 5. So there's 5 different flowers, A, B, C, D, E. Whatever there is, however many flowers. I'm just assuming from this 4 thing here that there would be 5 different labels. Maybe 0 to 4, which would be 5. But whatever. So these are the possible categories. So given these 2 pieces of information, the petal length and the sepal length, those 2 pieces of information is going to break us down to one of those, let's assume it's 5 flower types. All right? And the training data is going to say, okay, here's a petal length, here's a sepal length, whatever that is, and then here's what the right answer is. And what you're going to do, and we'll get to it here in a second with the way it gets trained, is it's going to go through that training data over and over and over and over again, adjusting itself a little bit each time until it starts making accurate guesses as to the correct label, the correct classification. Given the petal length and the sepal length, it guesses the right flower over and over and over again. So it's going to do that based on the X training data and the Y training data. Okay, the Y is the answers, the X is the inputs. Then we'll be able to test it using data it's never seen. So X test is the values. Y test is the answers to those values, what the actual classification is. All right, so that this line right here splits your data set into those 4 pieces. So you can use it. All right, so the standardizing the data, this makes sure all the values are kind of within a certain, you'll read about it in the chapter, but sometimes you'll have data sets where an example might be that, let's say it has a bunch of measurements in it, and some measurements are in millimeters, other measurements are in inches. It'll standardize it to be all on a same scale. That way you don't have data that's way out, a big number that looks big, but it actually isn't big. It just is a big value. The way it was measured is big relative to these other smaller values. So you might always operate, maybe the sepal length, for example, is always a very large value relative to the petal length. So what we might do is, for training purposes, we might say that we use the sepal length and we might use 10% of the petal length. Because we might just say that it's a scalar of 10 that just arbitrarily is extra large value. So we'll always just take 10% of it because the pattern should still exist. All right, so we create a scalar, we pass it the training data. We then will update our training data with a scaled version of it. It'll go through and balance it. Same thing, we'll do the same thing with our test data. All right, that's just cleaning the data up, making sure that we've given ourselves the best chance of getting that guy trained, having data that can be trained to that pattern, as opposed to having something that might have such weird values relative to each other that we might make too big of adjustments whenever we're updating our machine learning model that we never actually land on a good solution because the data is just too big. It makes a guess, you're off by 5,000, and then it over adjusts the neural network to hopefully get it less wrong next time. It brings the data much closer together. So that's all that's happening in here. Okay? So we have this thing called a classifier. So the classifier ultimately is our neural network. We don't have to write a neural network. It's already built in here. Okay, so we have this classifier. I don't know what the neighbors thing here. It's the input for this is the constructor for our classifier. It is taking in 3 neighbors. That might be something you can play with to get you better or worse values. So neural networks, once you have the tool, you can say, okay, well, I want it to run through 1,000 times, or I want it to have this many inputs or this many outputs or this many hidden layers. So there's a couple of different variables you can tweak on it to hopefully get you better results. So we'll swing back to that in a second here. So you build your classifier, and then what you do is you try to fit your X and Y training data. And what does that mean? This line right here is going to go through that data over and over and over and over again until your training data for X and Y becomes accurate enough. I'm not sure what the the threshold for fit is. It's probably not 100% because there's not a guarantee you'll always get 100% of the answer. So maybe the default accuracy for fit might be 90%, let's say. So it'll keep running until it gets to 90% of these guys right. So giving the row 0 of X train and the expected answer of row 0 of Y train, it makes its guess, it updates that model in whatever way the math says it should update it. You don't have to do any of this, it just does it for you. And it'll do that over and over and over again until this classifier has now updated itself such that it has a reasonable level of accuracy for that training data. All right. Now, we're going to make our prediction. Okay, and our prediction is off our testing data. So notice this X test here, this is data it has never seen before. Because I've only fit this thing to my training data. This testing data, this is just sitting there, it's never seen it before, and we're hoping that we have this classifier that's been kind of taught, he's learned. I can now feed some X data to that it's never seen before, and he will give me a prediction for the type of iris this is, and he'll get it right, or have a high % chance of getting it right. Make sense? All right, this guy will effectively run this classifier test across your entire test and your predictions. So it'll show you a visualization of it. Actually, I don't think it creates a visualization. I think it creates a data set. And then you can print out that data set to see what it ends up looking like. This is the visualization side of it. So it'll kind of show you what it actually predicted versus what the actual value was versus what it was predicted, and you should see in that visualization that your classifier got a very high percentage of it right when it made predictions on data it had never seen before. Make sense? Now this iris data is way more complex than the data I'm going to have you work with. But the thing is, it doesn't even matter because you didn't have to do any of the neural network stuff. Even though this looks like several lines of code, all this is saying, what do my inputs look like? What does my output look like? Give me my 4 data sets, clean it up, train it. Now I can start making predictions. All right, questions on how that works? Is there a certain
I know when you did the hack,
no. I mean, and the thing is, I don't even know what this guy would give me. Let's see, the code before into 75% training set, 25% test set. So tell me what because ultimately it doesn't look like from this code, at least we can choose that. This dot fit function, that guy trains it to maybe the best it can. So if my guess would be that this fit function, what ends up happening is sometimes you will get a situation where it just keeps going back and forth between 2 values. There's probably a way afterwards to then ask your classifier what it was trained to. It probably has some information. So whatever the K-neighbor classifier, he probably has some let's do something like this. And he'll tell us what his accuracy was after the fit. Yeah, so it's something called score. So score would return the mean accuracy on the given test data and labels. If you were interested. That will tell you how well it fit that neural network. So it's a neural network under the hood, but your book will call it a model. How well it was able to fit the model to your data. And, if it's data that doesn't really have a great pattern, then it might fit it to 13%. That's possible, right?
So I have a question.
Yep.
So actually, the model actually will be affected by the sequence of the testing data actually?
Could be, but that's hopefully going to be managed by the number of iterations, and also typically we aren't actually seeing it here, but this algorithm for this K-neighbor classifier, this guy, whatever that's using, probably does some randomization of the data.
Could be possible, say, once the first time you train is bad, and the second time it turned out good?
Well, I would say it's possible, but not probable. If you train it 10 times, I think you will probably get ultimately to a very similar fit, if not the identical fit. Usually once you train something, especially on a large data set, you end up storing the weights that, the neural network values. That way next time when you go to use your classifier again, you just load up its old values. You don't have to retrain it. Because in this case, training is probably going to take, 15 seconds or something, I'm guessing, not long. But for some data sets, training could be like a 3 hour, 5 hour, 2 day, it could be a long time. You only want to do that once. But you're right. I mean, feeding it in different orders could have some different early stage things, but if a pattern is there, the idea is you should start converging on that pattern. That's when, with traditional neural network algorithms like backpropagation, you might tweak certain things like the learning rate and stuff like that. That's kind of what I was mentioning earlier about normalizing the data, so all the data kind of looks similar in size. Otherwise, whatever the algorithm they're using to update the model might make overcorrections and never actually land on the right value on the inside, or where it's supposed to be. That makes some sense? Yes. We're all just about done.
For the movie, I just got to know that it was
Yesterday.
Yeah.
You gotta read Slack. There's even pictures on Slack from the movie.
Oh, I thought that was the movie that was being shown.
That was them watching the movie yesterday. They put pictures of them watching it. Yeah, it's pretty bad. Okay, questions about?
I have one question.
Yep.
So, just so I can look at the actual data set, where would I be able to find the iris data set?
Well, you actually probably can find it just a real quick Google search. I think Seaborn has it, but if you just do iris, it's a famous data set. Machine learning repository. Here's the attributes.
I looked on
Yeah.
a couple different websites, but
This looks like it might have it. Here it is. Iris CSV. There it is.
Does it just look like a flower or something?
It looks like a bunch of lines. Is it numbers?
Yeah, there's numbers in there.
It's like the Bible.
That's
That
the
is-
CSV.
Not quite.
So the part I'm still kind of confused about is like the where it's doing like the ILO,
3 columns of numbers.
We're just doing the what?
where it's doing the ILO, like, so like when it's doing, it's setting X to like the columns 0 to 2, so like that would be like the sepal length, sepal width, and sepal, or petal length. But then it was doing Y as like 0 to 4, so like
It wasn't doing 0 to 4. It was just doing 4. So this is 0, 1, 2, 3, 4. So that was bucket 4 for what it was grabbing there, and this was the X value. So your X training set were these inputs, and then your Y training set was this output.
can you wait? Okay, so can you go back to the textbook? Okay, so like when it's doing,
Actually, it
so
doesn't
it's
use the
doing
point 2.
Y,
Your X is actually just this. 0, 1, and 2. It's using those 3 datas, those 3 points for X, and this one label for Y. So it's omitting this in our data.
so it's
And that
looking
guy
at, so it's
is,
looking at the first 3 columns of
yeah, it's not working with pedal width here.
okay, yeah.
I'm guessing they maybe purposely did that because I'm guessing that pedal width must throw it enough of a curveball that it has issues fitting the model.
Okay, and then the Y was doing the 4, which means what?
That's the type of iris.
The
The-
name of the flower.
Yeah, so these are all versicolors. This is Setosa. These are all iris names.
Yeah, I just don't understand the syntax for it. So like if you,
Given these 3 inputs for X,
yeah.
this is the expected output for Y.
Yeah, but I mean like in the actual textbook.
Yeah, so given
I
these,
get that part.
okay.
I don't get the Y part. That one. Yes, that.
It says get me bucket 4.
Okay.
Just bucket 4.
Okay, which would be the 5th. Okay. Okay. Sorry.
Yeah, 0, 1, 2, 3, 4. Okay, make sense?
Yeah.
Okay, so like I said, I'll have the exam up with the questions hopefully tomorrow, hopefully early in the day tomorrow. I would expect, and depending on the data set that I have you use, or if I have you created, I might give you some starter code to work with, but we'll see. I have to see what the data set ends up being. I have 2 in mind, but I want to make sure that they will work well before I just give it to you. All right, questions about that? All right, so my suggestion then would be is to adjourn, head over to Highland House, and we can talk about your interesting Bible questions when we're over there. Sound like a good plan?